Hello, everyone. Thank you for watching the KiboCUBE Academy on-demand lecture series. This lecture is number 20 in the series, and the title is Introduction to Space Debris Problem and Countermeasures. My name is Toshiya Hanada, professor at the Department of Aeronautics and Astronautics, Kyushu University, Japan, and Vice Director at the International Center for Space and Planetary Environmental Science, Kyushu University, Japan. My research interest is to confirm whether we really must clean up the space junk out there, as in Planetes, a Japanese hard science fiction manga written and illustrated by Makoto Yukimura. To figure out the right answer to this question, I'm working on a project titled Long-Term Sustainability of Outer Space Activities, Space Debris Modeling, and Space Situational Awareness. With this introduction, then, I shall get started with this lecture. Here is the overview of this lecture. Here is the overview of this lecture. Chapter 1 introduces space debris in general. Then, Chapter 2 describes the current situation, whereas Chapter 3 describes the future concerns. Then, Chapter 4 introduces the guidelines we must comply with. Then, Chapter 5 provides information on tools available to the public. Then, Chapter 6 provides some useful references. Finally, Chapter 7 summarizes this lecture. Let's move on to Chapter 1, Introduction. What is space debris? Space debris are all non-functional human-made objects principally left in Earth orbit, which no longer serve a useful function. These include non-functional spacecraft, spent rocket bodies, mission-related debris, and particularly numerous in Earth orbit, fragmentation debris from the breakup of space rocket bodies and spacecraft. In addition to non-functional human-made objects left in Earth orbit, other examples of space debris include fragments from their disintegration, erosion, and collisions, or even faint flakes, solid-filled liquid expelled from spacecraft, and unburned particles from solid rocket motors. Space debris represent a risk to spacecraft. How do we find space debris? Radar and optical measurements from the ground can detect objects rather than 0.2 centimeter in diameter. If you stare at the sky using a telescope, then you may see something flying through the field of view. Objects that are bright or big can be observed from the ground. Objects rather than 10 centimeter are followed so that spacecraft can maneuver away from those objects. However, objects between 0.2 and 10 centimeter are observable but not tracked. They are too small to make accurate orbital predictions, so spacecraft must be protected from impact with those objects. How much space debris is out there? 5,728 launches have been conducted since the launch of Sputnik 1. As of 1st January 2021, the United States Space Surveillance Network cataloged 49,695 artificial objects in orbit above the Earth. Approximately 24,000 of them are still orbiting the Earth, including approximately 5,100 satellites in operational. The primary factors affecting the growth of the true Earth satellite population are the international space launch rate and satellite fragmentations. As of 4th July 2018, breakup debris have surpassed half the cataloged Earth satellite population, as illustrated in this slide. Also, approximately 3 out of every 4 payloads are no longer operational and constitute a separate but statistically important class of orbital debris, accounting for 24.4% of the cataloged Earth satellite population. The percentage of rocket bodies and mission-related objects is almost the same, approximately 10%. The remaining 2.3% originated from anomalous events. How long will space debris remain in Earth orbit? The answer to this question depends upon the altitude of the orbit, with common time frames being a few days if the altitude is less than 200 kilometers, a few years if the altitude is between 200 and 600 kilometers, decades if the altitude is between 600 and 800 kilometers, centuries if the altitude is greater than 800 kilometers, and forever if the altitude is 36,000 kilometers or greater. The picture on this slide is of Vanguard 1, the world's oldest known piece of space debris, launched on 17th March 1958 to observe the Earth's oblateness, continental drift, and upper atmospheric drag. Let's look at an example of what happens when a piece of space debris collides with a spacecraft. A mock-up satellite with dimensions of 20 centimeter by 20 centimeter by 20 centimeter got hit by an aluminum alloy solid sphere with a diameter of 3 centimeter and a mass of 39 grams. The impact velocity was 1.74 kilometers per second, which is close to the maximum relative velocity possible in the geostationary region. The mock-up satellite was totally fragmented, generating more than 2,400 fragments down to 2 millimeters in size. Since objects in low Earth orbit travel at velocities close to the first cosmic velocity, collision in low Earth orbit would be even worse than this example. Since the relative velocity in low Earth orbit is approximately 10 kilometers per second on average. So let's replace the energy when a 1 centimeter aluminum alloy solid sphere collides at the velocity of 10 kilometers per second with something around Earth. It has the same energy as a sports utility vehicle traveling at 4 kilometers per hour, or 30 kilograms safe hitting you at 250 kilometers per hour, which is close to the speed at which the Shinkansen slows down a little. Or a bowling ball hitting you at 500 kilometers per hour, which is close to the maximum speed of the Shanghai maglev train. A piece of debris with a diameter of less than 10 centimeters is generally untracked from ground-based measurements, but still have enough potential to cause mission-ending damage if colliding with operational spacecraft. Next, let's move on to Chapter 2, Current Situation. This slide displays the number of all objects in Earth orbit officially cataloged by the United States Space Surveillance Network. Low Earth orbit, LEO, includes resident space object with altitude within or crossing below 2,000 kilometers. Medium Earth orbit, MEO, resident space object with altitudes within or crossing the range from 2,000 kilometers to 35,586 kilometers. Geosynchronous orbit, GEO, resident space object with altitude within or crossing the range from 35,586 kilometers to 35,986 kilometers. And the remainder with altitude within or crossing the range from 35,986 kilometers to 600,000 kilometers, referred to as Super GEO. The effective number sums the fraction of each orbit that falls within the specified ranges. Catalogued objects without available orbital elements are excluded. This figure is illustrating that the lower the orbit is, the more space objects exist, and the number in LEO is reaching about 20,000 objects in 2022, the largest portion of objects in orbit. You can also see that there are some discontinuous increases in the number of LEO space objects, which are supposedly caused by either breakups of an object, collisions of two space objects, or deliberate destructions of space objects. This slide summarizes the total number of annual launches in red and cumulative launches in blue, counted for the entire world. The graph is indicating the number of launches in recent years are rapidly increasing and has already exceeded more than 100 launches annually. This is the result of today's accelerating commercial space development and utilization activities worldwide. Also, with the emergence of large constellations of small spacecraft in LEO, such as SpaceLink constellation. The number of launches as well as the number of space objects in LEO is increasing more and more, which could impose even greater importance of solving space debris issues. As introduced in Chapter 1, by far the most important category of man-made on-orbit object is satellite breakups, which now account for 42.6% of the total catalog on-orbit Earth satellite population. Since 1957, a total of 242 satellites are believed to have broken up. Breakups due to aerodynamic forces at or near reentry are treated separately from breakups by other factors, because aerodynamic breakups occur at the end of the satellite lifetime and therefore contribute nothing toward the orbital environmental past the very near term. The primary causes of satellite breakups are propulsion-related events and deliberate actions, although the cause for almost 1 in 4 breakups remains uncertain. Deliberate actions often associated with activities related to national security were formerly the most frequently occurring class. On average, the resulting debris from deliberate actions are short-lived. Propulsion-related breakups, currently the most frequent class, include catastrophic malfunctions during orbital injection or maneuvers, subsequent explosions based on residual propellants, and failures of active attitude control systems. Breakups of rocket bodies due to propulsion failures are usually more prolific and produce longer-lived debris than the intentional destruction of payloads, often due to the higher altitude of malfunctioning rocket bodies rather than mechanism of the explosive event. Breakups of the CIS block DM system of the near the Vasta SOD alleged motors are segregated from other members of the propulsion ensemble due to their high probability of fragmentation, which tends to overinflate the propulsion category to some degree. Omitting the SOD breakups equates the non-SOD propulsion and deliberate categories. Although it may appear obvious that a rocket body breakup should be classified under the propulsion category, rocket body events are carried as unknown until a failure mechanism can be confidently identified for that rocket body design and is associated with given rocket body event. Collision events currently account for only 2.5%, but as we will see later, we believe that collision events generate space debris, which increase the likelihood of further collisions, generating more and more space debris. French series collided with a debris fragment from a French Ariane 1 rocket body on 24th July 1996. This event was the first identified accidental collision between two catalogued objects. At this event, French series had its 6-meter-long stabilization boom severed. The colliding fragment was the size of a briefcase and traveling at a relative velocity of 14 kilometers per second. Following the collision, the satellite's onboard computer was reprogrammed for attitude control to be operational. The United States Iridium-33 and the Russian Cosmos 2251 ran into each other above northern Siberia on 10th February 2009. This event was first ever accidental collision between two intact objects. They were traveling at a relative velocity of 11.6 kilometers per second. By 1st August 2022, the United States Space Surveillance Network had officially cataloged 2,369 fragments. The estimated number of fragments, rather than 1 centimeter in diameter, exceeds 62,000. The event highlighted the orbital debris problem in low Earth orbit. 3 more accidental collisions between catalogued objects have been confirmed. Thor Burner 2A rocket body collided with a debris fragment from a Long March 4 rocket body on 17th January 2005. Cosmos 1934 collided with a debris fragment from Cosmos 926 in late December 1991. Bullets, a small laser-ranging reflector satellite, collided with a debris fragment from Phenyun 1C in January 2013. Now we see non-accidental collision in space. Events with ears colored red are accidental collision between catalogued objects, as I already presented, while events with green-colored ears are accidental collisions with uncatalogued objects. Remember that uncatalogued objects are generally less than 10 centimeters in diameter, but still have enough potential to cause mission-ending damage if colliding with operational spacecraft, as introduced in Chapter 1. Now let's move on to Chapter 3, Future Concern. First, we must recognize that the current situation is unstable. This unstable situation is sometimes called chain reaction or Kessler syndrome. The chain reaction is a scenario in which the density of objects in low Earth orbit is high enough that collisions between objects could cause a cascade. Each collision generates space debris that increases the likelihood of further collisions. This scenario has been proposed by Professor Rex at the Braunschweig University of Technology in Germany. Kessler, a NASA scientist, has also proposed this scenario, but called it collisional cascading. One implication is that the distribution of debris in orbit could render space activities and the use of satellites in specific orbital ranges unfeasible for many generations. What may cause the chain reaction? As I already introduced in Chapter 1, space debris are all non-functional, human-made space objects. So space debris can be generated by new launches, satellite fragmentation, such as collisions and explosions, and disintegration of satellite materials. On the other hand, space debris can be reduced by natural decay due to the upper atmosphere. Alternatively, space debris reduction techniques include having the debris returned to the ground or escaped from the Earth's gravity. If the rate of debris generation exceeds the rate of debris reduction, then the chain reaction or collisional cascading may happen. What I show here is an example of the instability of the current debris population in low Earth orbit. This example used the initial population as of 1st January 2006, including all 10 centimeter and larger objects crossing LEO. This example also allowed no new launches beyond 1st January 2006 and set future explosions to 0. This is so to reach a consensus on the stability or instability of the current debris population in LEO. With this scenario, the instability can happen due to chain reaction or collision cascading. So what you see here is population growth in LEO. Intact and mission-related objects in blue and explosion fragments in orange decrease over time due to atmospheric drag, and so does the total number displayed in red. This is true, but only at the beginning of the projection. The total number increases as collision fragments colored in green are newly generated. As shown in Chapter 2, we have continued outer space activities after 1st January 2006. In addition, many on-orbit satellite fragmentations have happened. Taking these into account, the growth rate of the debris population in LEO is likely to be greater than what is shown in this slide. Now we see the effectiveness of space debris mitigation. This example used the initial population as of 1st January 2013. This example also set future explosion to 0, but allowed new launches beyond 1st January 2013. The term regular launches means repeating the insertion history of the past 8 years from 1st January 2005 to 31st December 2012, which is called business as usual. Space debris mitigation guidelines of the Interagency Space Debris Coordination Committee, which will be described later, has recommended that spacecraft or orbital stages that are terminating their operational phases in orbits that passed through the LEO region or have the potential to interfere with the LEO region should be deorbited, or, where appropriate, maneuver into an orbit with an expected residual orbital lifetime of 25 years or shorter. PMD is an acronym for post-mission disposal, meaning this guideline, which is also known as the 25-year rule. And the percentage before PMD represents the probability of success. The guideline also has recommended that the probability of success of the disposal should be at least 90%. However, we still see population growth even with a success rate of 90%. The reason why disposal is not effective is the chain reaction or collisional cascading. Therefore, we believe that environmental remediation is necessary. This example used the same initial population and future insertions as the previous example. Also, the success rate of PMD is fixed at 90%. ADR here is an acronym of active debris removal, and ADR 2025 and ADR 2025 means starting ADR from the year 2025. The last 2 digits after slash represent the number of objects removed every year. This example preferentially removed object with a high product of collision probability and mass. We may expect environmental remediation when 8 high-risk objects can be removed every year. Removing 2 or 5 high-risk objects is not effective, however. Now we see an example of the impact of a large constellation of satellites. This example used the same initial population, future insertions as the previous examples. The success rate of PMD is also fixed at 90%. The difference from the previous example is a large constellation of satellites at an altitude of 1,200 kilometers. The large constellation contains 1,000 satellites, with 50 satellites evenly distributed in each of the 20 orbital planes. The inclination of all the orbital planes is assumed to be 75 degrees. Each satellite in the constellation has a lifetime of 5 years, a mass of 150 kilograms, and an average cross-section area of 3.0 meters squared. The constellation is assumed to begin its construction in early 2016 and to start its service in early 2020. Also, the service is assumed to continue for 30 years so that 200 satellites were deployed every year until the end of service. When construction starts, the difference from the case without the constellation increases. After the service ends, the difference from the case without the constellation decreases. But the difference continues to remain instead of becoming zero. Note that environmental remediation is not conducted for this example. Now I shall introduce guidelines we must comply with. The Interagency Space Debris Coordination Committee has recommended space debris mitigation guidelines and provided existing practices that have been identified and evaluated for limiting the generation of space debris and the environment. The guidelines cover the overall environmental impact of the missions with a focus on the following measures: limit debris released during normal operations, minimize the potential for on-orbit breakups, post-mission disposal, and prevention of on-orbit collisions. The Scientific and Technical Subcommittee of the United Nations Committee on the Peaceful Use of Outer Space developed a set of recommended guidelines based on the technical content and the basic definitions of the IADC Space Debris Mitigation Guidelines, taking into consideration the UN treaties and principles on outer space. The guidelines were adopted by consensus in February 2007, and the full COPIUS endorsed the guidelines in June 2007, followed by General Assembly endorsement later in 2007. The Space Debris Mitigation Guidelines of the SDSC of the UN COPIUS consist of 7 guidelines to be considered for the mission planning, design, manufacturing, and operational phases of spacecraft and launch vehicle orbital stages. From now on, I will introduce the guidelines, but I will skip guideline 7, that is for the geosynchronous Earth orbit region. Guideline 1 limits debris released during normal operations. Space systems should be designed not to release debris during normal operations. If this is not feasible, the effect of any release of debris on the outer space environment should be minimized. During the early decades of the space age, launch vehicle and spacecraft designers permitted the intentional release of numerous mission-related objects into Earth orbit, including, among other things, sensor covers, separation mechanisms, and deployment articles. Dedicated design efforts prompted by the recognition of the threat posed by such objects have proved effective in reducing this source of space debris. Guideline 2 minimizes the potential for breakups during operational phases. Spacecraft and launch vehicle orbital stages should be designed to avoid failure modes, which may lead to accidental breakups. In cases where conditions leading to such a failure is detected, disposal and passivation measures should be planned and executed to avoid breakups. Historically, some breakups have been caused by space system malfunctions, such as catastrophic failures of propulsion and power systems. By incorporating potential breakup scenario in failure mode analysis, the probability of these catastrophic events can be reduced. Guideline 3 limits the probability of accidental collision in orbit. In developing the design and mission profile of spacecraft and launch vehicle stages, the probability of accidental collision with known object during the system's launch phase and orbital lifetime should be estimated and limited. If available orbital data indicate the potential collision, adjustment of the launch time or an on-orbit avoidance maneuver should be considered. Some accidental collisions have already been identified. Numerous studies indicate that as the number and the mass of space debris increase, the primary source of new space debris is likely to be from collisions. Collision avoidance procedures have already been adopted by some member states of the United Nations and international organizations. Guideline 4 avoids intentional destruction and other harmful activities. Recognizing that an increased risk of collision could pose a threat to space operations, the intentional destruction of any on-orbit spacecraft and launch vehicle orbital stages or other harmful activities that generate long-lived debris should be avoided. When intentional breakups are necessary, they should be conducted at sufficiently low altitudes to limit the orbital lifetime of resulting fragments. Guideline 5 minimizes potential for post-mission breakups resulting from stored energy. To limit the risks to other spacecraft and launch vehicle orbital stages from accidental breakups, all onboard sources of stored energy should be depleted or made safe when they are no longer required for mission operations or post-mission disposal. By far, the largest percentage of the cataloged space debris population originated from fragmentation of spacecraft and launch vehicle orbital stages. Most of those breakups were unintentional, many arising from the abandonment of spacecraft and launch vehicle orbital stages with significant amounts of stored energy. The most effective mitigation measures have been the passivation of spacecraft and launch vehicle orbital stages at the end of their mission. Passivation requires the removal of all forms of stored energy, including residual propellants and compressed fluid, and the discharge of electric storage devices. Guideline 6 limits the long-term presence of spacecraft and launch vehicle orbital stages in the low Earth orbit region after the end of their mission. Spacecraft and launch vehicle orbital stages that have terminated their operational phases in orbits that passed through the LEO region should be removed from orbit in a controlled fashion. If this is not possible, they should be disposed of in orbits that avoid their long-term presence in the LEO region. When making determination regarding potential solutions for removing objects from LEO, due consideration should be given to ensuring that debris that survives to reach the surface of the Earth does not pose undue risk to people or property, including through environmental pollution caused by hazardous substances. The United Nations Committee on the Peaceful Use of Outer Space adopted by consensus a preamble and 21 guidelines demonstrating how states collaborate mutually to prioritize space sustainability. The guidelines for the long-term sustainability of outer space comprise a compendium of internationally recognized measures for and commitments to ensuring the long-term sustainability of outer space activities. The preamble of the guidelines defines the long-term sustainability of outer space activities, explains their voluntary and non-legal binding status, and shares how the guidance they provide is to be reviewed and updated. Now, the next chapter provides information on tools available to the public. The NASA Debris Assessment Software, DAS utility provides assessments that can verify compliance of a spacecraft at stages and or payload with NASA's requirements for limiting debris generation, spacecraft vulnerability, post-mission lifetime, and entry safety. Successful verification of a design in DAS demonstrates compliance with NASA debris mitigation requirements. Historically, DAS analysis has proven acceptable in meeting compliance requirements of many other agencies in the United States and around the world. It does not address the inherent design reliability facets of NASA requirements, but addresses all Earth-related orbital debris requirements that make up the bulk of the requirements in the NASA Technical Standard 8719.14C. The ESA Debris Risk Assessment and Mitigation Analysis, DRAMA, is a comprehensive tool for the compliance analysis of a space mission with space debris mitigation standards. For a given space mission, DRAMA allows analysis of debris and meteoroid impact flux levels, reorbit and deorbit fuel requirements for a given initial orbit and disposal scenario, geometric cross-sectional computations, re-entry survival predictions for a given object of user-defined components, and associated risks on ground for at the resulting impact ground swash. The CNES semi-analytic tool for end-of-life analysis, STELLA, has been designed to support the French Space Operations Act. It reflects the standard concerning the protection of LEO and GEO regions, and provides the user with tools to assess the compliance with the requirements. The software allows efficient long-term propagation of LEO, GEO, and GTO based on a semi-analytic models and assessment of protected regions criteria. STELLA produces a report file that summarizes the computation and optionally an FMS file. The NASA Orbital Debris Engineering Model, ODEM, is appropriate for those engineering solutions requiring knowledge and estimates of the orbital debris environment. The latest version, ODEM 3.2, has been updated to include fragments from Cosmos 1408 and satellite test conducted by Russian Federation on 15th November 2021. The ESA Meteoroid and Space Debris Terrestrial Environment Reference, MASTER, allows to access the debris or meteoroid flux imparted on a spacecraft on an arbitrary Earth orbit. MASTER also provides the necessary computational and data reference for ESA DRAMA and needs to be installed before ESA DRAMA is installed. These are the major tools available to the public for the evaluation of space debris-related issues. I hope this information is useful for your further investigation on this topic. Now, this next chapter provides some useful references. The International Academy of Astronautics has published a handbook for post-mission disposal of satellites less than 100 kilograms. The handbook identifies space debris mitigation guidelines and engineering options to satisfy requirements for post-mission disposal. The handbook is applicable to satellites less than 100 kilometers in mass, including CubeSats. The handbook was written by experts in the field of space debris mitigation and spacecraft design. The Joint Space Operations Center, JSPOC, would like to engage as early as possible with all CubeSat launch entities and owner-operators to discuss mission requirements, negotiate optimal support, and establish lasting relationships that will ensure mutual operational success. The JSPOC offers the following recommendations for CubeSat launch entities and owner-operators to consider as they conduct CubeSat planning. Satellite identification is extremely difficult to determine without initiative taken by the launch entity and/or owner-operator. Satellites should have some maneuver capability to facilitate conjunction avoidance on orbit. Satellites should be built to allow controlled reentry or expedited uncontrolled reentry to minimize the threat of individual CubeSats beyond the satellite mission life. Finally, we will wrap up this lecture. The current LEO debris population is expected to increase even with no new launches and explosions. Even with a good implementation of the commonly adopted mitigation measures, the LEO debris population is still expected to increase. Environmental remediation is required to prevent an increase in the LEO debris population. We must understand the above situation and comply with the space debris mitigation guidelines to ensure the sustainability of outer space activities. Thank you for watching this lecture number 20. Stay tuned for more lectures in the series.